All right, so today I want to finish up what is that, chapter 4, with a discussion of the regular representation. And this is the end of the theory part of representation theory of finite groups. And well, you could really say that we've already ended it at this point. The regular representation is just a representation that has some nice properties. Okay, but after I finish this up, I'm gonna get into the Fourier analysis stuff. So I'll be doing that today. All right. So let X be a finite set. I think we'll assume that all throughout, although uh, pretty soon we'll be changing X to a finite group. So I think the notation will be ditched. But anyway, we can build a vector space with basis X and just the obvious way, right? Just take a formal span of the elements of X. So formal sums or formal power series, whatever, of well, it would be formal sums because X is a finite set uh, of elements in X. And we can give it an inner product. So again, we're just using the obvious uh, choice here. This can be the sum over X and X of AX BX conjugate. And if you're a physicist, then you'll go the other way. You'll put the conjugate on the A. Okay, so let's define the representation that we're going to discuss today. Let G be a finite group. Maybe I can stop writing that. We'll just always assume G is a finite group. The regular representation of G is the homomorphism L sending G to the general linear group where our vector space is this formal one where the finite set is taken to be the elements of the group. Defined by LG acting on an element of this formal span. How does it act? Well, it acts by left multiplication. And we define it so that it's linear. So another way to write this would be as the sum over X and G of CG inverse X times X. So maybe I'll explain this one more time. So I can do a sort of change of variable type thing here, where I can define X to be equal to G times H, so that this quantity here becomes X, and this H here becomes G inverse X here. And the reason that this summation, we can now write it as being over X is because, well, as H ranges over G, well, so does G times H. So you're still summing over the entire group regardless. Okay, so LG is just left multiplication essentially, and we with the caveat that we ignore the constants in our formal sums. There. All right. So, oh, by the way, in the literature, this thing here, assuming X is a group, this thing here is what I've seen be called the group algebra before. And Steinberg's book, he takes this thing L of G, which is the set of all functions from G to C, and he calls that the group algebra. So I think that there is some equivalence between these two things, but I don't see it immediately. Okay, so why do we care about this representation? Well, the regular representation contains all the irreducible representations of G as constituents. Okay, so maybe this is the first step if you want to know all the irreducible representations of some finite group. Maybe a good first step is to write out the regular representation because it contains every single irreducible representation. Okay, so we can sum this up in a theorem concretely. Let L be the regular representation of some group G, finite as usual. Then the decomposition, L is equivalent to phi1 d1 times through phi s ds times. So this holds where the phi I are irreducible representations with degree given by this di quantity. So remember this notation here just means phi1 summed with itself d1 times. Okay, so here's proof. So first observe that the character of the regular representation is given by the order of G when G is equal to 1 and 0 when G is not 1. So to see this, let's observe that LG acting on an arbitrary element of this formal span is equal to, well, we've already written it out. This is CG inverse X times X. And this is a constant multiple lambda sum over H and G CH H. When is this true? This is true whenever lambda CH is equal to CG inverse H for every H. Why? Because these elements of the group are the basis for the space. Right? So if we set this equal to the right-hand side here, then we get exactly this condition, just by linear independence. Okay, so this can only be true if, so this is only true if either G is 1 or lambda is 0. So that means that the only eigenvalue of LG with G not equal to 1 is lambda equals 0. And when, okay, let me write that. So only eigenvalue with G not equal to 1 is lambda equals 0. So in particular, that implies that the trace is going to be 0. So in other words, XL of G, which is the trace of LG, is 0 for this case. So that proves the first part of this statement. And when G is equal to 1, all eigenvalues are lambda equals 1 because LG is then the identity, right? So L is a homomorphism. Homomorphism will always send the identity to an identity. Right? So that means that XL of G equals 1 is the trace of the identity, which is equal to the order of G. Okay, that proves this first statement here. So let's let I denote the character of phi I. All right, then we use the results of last section. We compute this inner product, and that'll tell us how much of this I representation is contained in the sum. So this is 1 over the order of G, sum over G and G. This is just the definition of the inner product here. I'm trying to speak and write at the same time. Okay. So what is this? Well, from the result that we just showed here, we know that this chi L of G will be 0 unless G is 1. So that's the only term in the sum that survives. And in that case, this is the order of G. So the only thing left is, well, the order of G's will cancel. And we're just left with chi 1 bar of G. And what is chi 1? Well, that's the degree of, G is 1. Chi I of 1. But what is chi I of 1? Well, it's the degree of representation I, right? So this is the degree of phi I. There's a conjugate there, but the degree is real, so it's irrelevant. And this is what we define to be di. Okay, and that completes the proof, because according to our decomposition theorem from last time, this tells us how much of the I representation is in the representation that we started with. So the representation associated to this chi L character, which is the regular representation. Okay, so a corollary of that will answer your question from last time, Logan. The order of G is always equal to the sum of the squares of the degrees of the irreducible representations. And the proof is very simple. So by the theorem, we know that chi L is d1 times chi 1, blah, 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 ds through chi s. So where does this come from? Well, the character of a direct sum of representations is just the sum of the characters. There was d1 copies of the phi 1 representation, ds copies of the chi s representation, so on. Okay, so then all we have to do now is evaluate at 1. What we get d1 chi 1 of 1 summed all the way through ds chi s of 1. And this chi 1 of 1, well, that's the degree of the first representation, that's d1. And so we're left with d1 squared, and same thing all the way through ds. And so that shows, since this is the degree of the regular representation, which is order of G, according to our formula, that shows that the order of G is the sum of the squares of the degrees of the irreducible representations. Okay, any questions so far? All right. So that is pretty much everything I wanted to go over as far as the theory goes. This regular representation is just a very nice representation. It contains all of the irreducible ones. And now what I'd like to do, start in the next chapter, which is our first real application here, which is Fourier analysis on finite groups. All right, so let's start with a very simple definition we all already know. A function f from the integers to the complex numbers is said to be periodic with period n if f of x is equal to f of x plus n for all x and z. Okay, so one thing to note is that the periodic functions are in bijection with the elements of L of Zn, so with the elements of the group algebra of Zn. So in other words, periodic functions, we can get from a periodic function to an element of L of Zn and vice versa. So why is this the case? Well, first of all, let me just remind you, this is all functions f from Zn to C. And so why is this the case? Well, periodic functions are functions that are constant on equivalence classes modulo n. And so they're essentially functions that map the integers modulo n to complex numbers. So you can kind of see how the bijection comes out there. Okay, so the irreducible characters of Zn, the irreducible characters of Zn. These things, by the way, remember they form a basis for this L of Zn thing. They are given by the nth roots of unity. In the following way. So the character, the kth character, evaluated at the m integer modulo n is equal to e to the 2 pi I km over n. So all of the irreducible characters fit this description for the cyclic group Zn. And it follows from our decomposition theorem from last time that, well, actually, this just follows from the fact that the irreducible characters form an orthonormal basis for this space. It follows that f can be written as a sum in the following way. Okay. And this is probably starting to look a lot like what you're familiar with, which is the Fourier transform. Fourier transform, let me write it this way, f hat from Zn to C of some function f, also from Zn to C, that'll change a little later, is defined by the following equation. So this is n times the inner product of f with chi m, which is the sum from k equals 0 to n minus 1, f applied to the residue class k, e to the minus 2 pi I km over n. So this is definition of our inner product that we've been using. And I've multiplied by this n because that's what Steinberg does, but ultimately amounts to a convention. Okay, so in that case, that implies that f is 1 over n times the sum from k equals 0 to n minus 1 of the Fourier transform evaluated at the residue class of k times the kth character. Right? And that follows from this piece here.
It's not important, but from your second to last line, are you forgetting an n in front of the sum? Or am I thinking about this?
Coming from here.
And then what about the next sum?
Or
the next
okay.
equal sign, excuse me.
Yeah, so there's a 1 over n.
There's 1 over, and that's what I was thinking. Okay.
Yeah, exactly.
Like 1 over the size of the group sort of thing.
Yeah, exactly. Yeah. Okay. So this thing here, by the way, is sometimes called the Fourier inversion formula. It's essentially telling you how to compute the inverse Fourier transform. Okay. So this Fourier transform on cyclic groups is actually used in signal and image processing. The idea is that the values of the Fourier transform correspond to the wavelengths associated to the wave function f. So what you do is, well, you take all the Fourier transforms at all the integers modulo whatever, and you set all sufficiently small values, so sufficiently small Fourier transform coefficients equal to 0. And what that does is it compresses the wave. And once you apply the inverse Fourier transform, you get back to something that looks close enough to your original wave function. Okay, so that's one place this is used that I wanted to mention. It's in Steinberg, which I thought was interesting. Okay, so let's continue on. So again, let G be a finite group, and let A be the elements of the group algebra. Then the convolution star B, which is a map from G to C, so it's another element of LOG, is defined by A star B evaluated at X. It's the sum over Y and G. A evaluated at X, Y inverse, B of Y. Okay. So the fact that this thing is a product on this L of G thing, so this group algebra, explains the name group algebra, right? It explains why we call this thing an algebra. Right? It's an algebra equipped with the product of convolution. But here's a question. Why equip L of G with convolution? What's the motivation? Well, first of all, every G and G produces a corresponding delta G in the group algebra. Right, this is the thing. This is the Kronecker delta function, right? It's 1 whenever the element you're applying it to is G, and 0 otherwise. And delta G convoluted with delta H, well, this is the sum over Y and G by definition, delta G X, Y inverse, delta H of Y. So the only terms that survive are when Y is equal to H and G is equal to XY inverse, which becomes XH inverse. So if x is equal to gh, right? That's inverting this here. Then this thing is equal to 1. And otherwise, it's equal to 0. What does this tell me? This tells me that delta g convoluted with delta h is equal to delta gh. So this is saying that this thing is another Kronecker function uh, uh, with the argument here gh. So it seems like this is a pretty natural product, first of all, to put on the space, given this this condition here. But moreover, recall that if A and B are elements of the group algebra, then A can be written in terms of these delta functions. Likewise for B, because these delta functions form a basis for this space. So in order to make L of G into an algebra, well, this distributive law has to hold. This distributive law, I'm going to sum over two things at once here. So I've written out both of these sums, well, the second one in terms of H, right? And I've assumed that the distributive law holds. So this is just some product here. And this is a sum over GH and G of A of G, B of H. And whenever this is the convolution, we get delta GH. And what that allows us to write is that this is the sum over X and G of the sum over Y and G of A of X, Y inverse, B of Y, delta X. So that's just a couple of substitutions here. So what is it? Y equals H and X equals GH. And then you do the usual argument where the sum can be replaced by the new variable because it goes over the entire group. Okay, and this thing here is exactly the convolution of A with B. Okay, so what does this tell us? Well, first of all, that was just the motivation for why we choose the convolution. But what does all this say? Well, it just says that L of G is an algebra. So it has pointwise addition for the sum. You can do scalar multiplication of the functions, and you still get another function here. And the convolution is this multiplication. So maybe I should add, moreover, delta 1 is the multiplicative identity. Okay. So remember how we denoted the class functions on G by Z of L of G? So remember, the class functions were the functions which are constant on a conjugacy class of G. Okay, so the center of an algebra A consists of all A in the algebra such that AB is BA for all B in the algebra. And my claim now is that, sorry, I was supposed to mention that this is usually denoted Z of A. And my claim is that this notation is now unambiguous, meaning that the center of the group algebra is indeed the set of all class functions. So suppose, I should write that. So the class functions form the center of L of G. Okay, proof. Suppose F is a class function. So we're going to do proof by containment in both directions. Let's let A be an element of L of G. What we want to do is we want to show that A and F commute with each other. Well, A convoluted with F evaluated at X. This is the sum over Y and G. This is just the definition of convolution. Okay. And since F is a class function, it's invariant under a conjugation in the argument. Definition of a class function. So this is F of, let's call it X, Y, X inverse. And now we can do our substitution trick again. We sum over Z and G of A of Z, F of X, Z inverse. And what is this? Well, this is nothing more than F convoluted with A evaluated X. So we have that if F is a class function, well, then it commutes with every element of the group algebra. Okay. So now we need to go the other direction. Now suppose F convoluted with A is A convoluted with F for all A in the group algebra. And let's show that this thing is a class function. So observe that F of GH is equal to the sum over Y and G of F of GY inverse delta H inverse of Y. Okay, so this should require a little explanation, I think. Okay, give me one moment. Let me make sure I understand this. So this is 0 unless Y is equal to H inverse, right? And if that's the case, then we get F of GH here. Okay, good. So this is equal to F convoluted with delta H inverse of G. Right, so this is the definition of a convolution. And then this is equal to, since F commutes with every element of the group algebra, delta H inverse, delta H inverse convoluted with F applied to G. So we should be thinking about this like this. And this is equal to the sum over Y and G of delta H inverse G Y inverse F of Y. And this is just F of HG. Right? So when H inverse is equal to GY inverse, that's when this thing is non-zero. It's equal to 1. And so we solve for y, right? And we get y equals gh, and so this is oh sorry, other way, hg, and so this is f of hg. Okay, so that tells us that uh, the argument of f is cyclic. So in other words, f of gh is equal to f of hg whenever f commutes with everything in the group algebra. That's not what we wanted to show. We wanted to show that this thing was a class function, but this property gives us exactly that. So if you conjugate an h by a g, well, you can just cycle according to this property here. This is h, g inverse g. And of course, g inverse g is just the identity. And so that we're left with f of h. And so that implies that f is a class function. And that completes the proof. So the space of class functions is exactly the center of the group algebra. So our notation there is unambiguous. Okay, so let's take a look at how this Fourier theory looks on finite abelian groups. So let G be a finite abelian group. So class functions on G are exactly the same thing as just functions on G, right? Because we're assuming the group is abelian, right? And that's going to imply that implies that L of G is exactly the center of G. Because the group's already abelian. Here, yes. So the dual group of G is the set G hat of all irreducible characters. G to C star. So remember, an irreducible character is just the character of an irreducible representation. That's what the definition of irreducible character is. For finite abelian groups, remember we showed that the degree of an irreducible representation is always 1. And whenever the degree of an irreducible representation is 1, well, the character just turns out to be the representation. And so that's why we have this C star here. Okay. Here's a fact. You can check this. I won't. It's not hard. This is indeed an abelian group. Under pointwise multiplication, yeah, it's a group under pointwise multiplication. I'm not going to prove it because we don't actually use this fact anywhere. But if you're curious and you want to work it out, it's not hard. Okay, here's an example with G equal to the integers modulo n. The dual group is the set of the characters x0 through xn minus 1 that we defined before. They're given by this formula here. And it's easily verified that the map that sends an integer modulo n to the irreducible representation chi k is an isomorphism. In other words, G is isomorphic to the dual group. And it actually turns out that this is always the case for a finite abelian group. So every finite abelian group is a direct product of cyclic groups. And from that fact, it follows that this will always hold because of the fact that it holds here for the cyclic group. Okay, so let's generalize a little bit our definition of the Fourier transform that I gave before. So before I gave it just for the cyclic group, let's generalize it to any finite abelian group. The Fourier transform will now go from G hat to C. So it goes from the dual group to C. This is the Fourier transform of a function mapping the group to C. It is defined by f hat of chi, right? Chi is an element of the dual group, is equal to the order of G, so for the cyclic group that was N, times the inner product of f with chi. And this is the sum over G and G of f of G, chi of G bar. Okay, so the definition I gave before used that isomorphism between the group and the dual group to write both the function and the Fourier transform as functions from Zn to C. Okay, so these coefficients here are sometimes called Fourier coefficients, by the way, because you can write f in terms of these things. Okay, so example, if chi and theta are in the dual group, then the Fourier transform of chi applied to theta is equal to the order of G, inner product of chi with theta. Yes, okay. So let me just point out where we're taking the Fourier transform of chi here. So that means that the Fourier transform of chi is an element of, well, it takes an element of the dual group. Elements of the dual group are the irreducible characters. So this makes sense here. And this is equal to, well, just by our orthogonality relations that we had before, this is order of G if chi is equal to theta and 0 otherwise. So that's just orthogonality relations we proved 1 or 2 sessions ago. So that implies that the Fourier transform of chi is equal to the order of G times this delta function, delta chi. Okay, so Fourier transform of an irreducible character is just the order of the group times the delta function. If f is in the group algebra, then we can write it as 1 over the order of G times the sum over chi in the dual group, Fourier transform of chi times chi. So this is what I was saying before. The reason these things are called Fourier coefficients is because of this Fourier inversion formula here. So the proof is not hard. It's a little computation. F is the sum over chi and the dual group, inner product of f with chi times chi. Right? Why is this? Because these chi things form an orthonormal basis for the group algebra here. And this is equal to 1 over the order of G, sum over chi in the group algebra, the order of G, F, oops, that should be an F, inner product with chi times chi. So I've just multiplied in order of G here and divided it out over here. And of course, this is equal to 1 over the order of G, sum over chi, and the group algebra, the Fourier transform of F applied to chi times chi. That's just the definition here. Okay, and that completes the proof. So here's a proposition. The map P sending the group algebra of G to the group algebra of the dual group given by the Fourier transform is an isomorphism of vector spaces. In other words, it's an invertible linear map. So again, proof is really, really easy. Let's call the order of G n. Then T of C1 F1 plus C2 F2 applied to chi. We need to show that this is C1 T of F1 plus C2 T of F2, all that whole thing applied to chi. Well, this is the Fourier transform of this whole thing here applied to chi. And this is equal to n, inner product C1 F1 plus C2 F2 with chi. Okay, that's our definition of the Fourier transform. And this is C1 n F1 inner product with chi. So I'm just using the linearity of the inner product now. And this is C1 Fourier transform of F1 applied to chi. That's the definition of the Fourier transform here. C2 Fourier transform of F2 applied to chi. And so what we have is that C1 F1 plus C2 F2, that Fourier transform is equal to C1 F1 Fourier transform plus C2 F2 Fourier transform, i.e. T is linear. Okay. So injectivity is very easy, right? If TF, which is Fourier transform, if that's equal to 0, well, by the Fourier inversion formula, obviously this thing is also 0, right? Everything has a Fourier transform in it. So this thing will also be 0. So that implies that T is injective, and to see that surjective, well, it just follows from the fact that the order of G is equal to the order of the dual group, right? Because then these spaces are equal in dimension. And so surjectivity follows. And that implies that T is an isomorphism. So in terms of signals, I guess you would say the time domain is kind of in some sense isomorphic to the frequency domain. Okay, so you can make this L of G space, this group algebra, into an algebra, right, using this convolution like we did before. But you can also just use pointwise multiplication. So what the Fourier transform does is it gives an isomorphism between these two structures. And specifically, it takes convolution to pointwise multiplication. So we know this as the convolution theorem. So the Fourier transform satisfies Fourier transform of the convolution is the product of the Fourier transforms, pointwise. Here's the proof. Again, straightforward computation. Let's set n equal to the order of g. Then we have that the Fourier transform of the convolution applied to chi is n times the inner product of the convolution with chi. That's my definition of the Fourier transform. And now I apply the definition of the inner product here. This is n times 1 over n, the sum over, that should be an x and g of the convolution of a with b evaluated at x, chi evaluated at x, complex conjugate. So definition of the inner product. These two things cancel, and we're left with the sum over x and g. And I'm going to write this chi out here like this. And now I'm going to write in the convolution. Okay. So now I'm going to swap the order of the summations. I can do that. They're finite sums, so no big deal. No convergence issues to worry about here. And now I'm going to define z to be xy inverse and do that whole substitution argument again. So this is the sum over y and g of b of y, sum over z and g of a of z, chi z y bar. Okay. And now, since let's see, yeah, since I'm assuming my group is abelian, these characters will actually break up into a product of characters. And so think about the character being given by the roots of unity, right? That root of unity I can always break up into a product when I have a sum in the exponent. Okay, so right here the group operation is being denoted by multiplication, but in the cyclic group case this would be a sum, and it's so that fits my description. Okay, but anyway, this will always split up as a product of characters. So we get b of y, chi of y bar, sum over z and g of a of z, chi of z bar. And now we are pretty much home free. Let's change the order here, right? And then this is equal to n inner product of a with chi times n inner product of b with chi. And that's just the Fourier transform of a applied to chi times the Fourier transform of b applied to chi. And so, in other words, Fourier transform of a convolution is the product of the Fourier transforms. So that proves our convolution theorem. Okay, so I want to end today with just an example. I want to put everything back in the perspective of the integers. So let's let f and g be functions that send the integers to the complex numbers. And let's assume that they have period n. So what's the convolution in this case? Well, the convolution applied to the equivalence class m modulo n is the sum k equals 0 to n minus 1 of f of m minus k g of k, and that's the convolution formula that we're probably familiar with. And the Fourier transform, well, this is just the sum from k equals 0 to n minus 1 of f of k e to the minus 2 pi I k m over n. So again, Fourier transform formula that we're probably used to. This exponential here comes from the character of the cyclic group. And we can write f as 1 over n by the Fourier inversion formula. 1 over n, the sum from k equals 0 to n minus 1, the Fourier transform evaluated at k becomes e to the 2 pi I k m over n. And by the convolution formula, we have that Fourier transform of this convolution here is given by the product of the Fourier transforms. So why is this useful, by the way? It's because in practice, it's more efficient to compute the product of the Fourier transforms and then apply the Fourier inversion theorem than it is to compute the convolution here. Okay, so that's all I wanted to say today. Next time, I'm going to do the application of all this Fourier analysis stuff to graph theoretical problems. I believe we will touch on Cayley graphs and possibly things like adjacency matrices, which is related to a paper that I just put out. So hopefully there's a connection there. Any questions?
Yeah, can I ask a question?
Yeah, go for it.
In signal processing, because we do signal processing, right?
Yeah.
They use this orthogonality, basically. They use orthogonality of the complex exponential to derive every formula, like inverse Fourier or Fourier transform. Mm-hmm. So is orthogonality hidden somewhere, like behind everything you've shown here, or do we need orthogonality only in do we need orthogonality in fact?
Well, it follows here. So the orthogonality, first of all, follows here from the orthogonality of the irreducible characters, right? That's where it's coming from here. Right. And the irreducible representations happen to be these exponentials. Okay, do we need it? I want to say is you definitely need it to be a basis, right, in order to get this Fourier inversion theorem. I want to say the orthogonality is hidden somewhere. I don't know exactly where.
Or is it just another way to express orthogonality in a kind of hidden way, right? Because this is the principle of Fourier decomposition, as I remember.
Yeah. I don't know exactly how to answer your question.
Yeah.
But I know a little bit in signal processing, they actually use frames, where instead of having this like orthonormal basis elements, you actually have some sort of spanning redundancy. So you can actually lose some of your signal, but still reconstruct your element. So I guess it depends on the context. Sometimes you probably have orthogonality and other times you don't.
Yeah. All right. Any other questions?